Então, muito obrigado a todos estarem aqui e a aqueles que estão em casa, eu não sei quando é que devo ligar esta câmara, e por terem a paciência de aguentar os primeiros 15 minutos, estivemos aqui com alguns problemas técnicos. E agora, se calhar, vou passar então para falar em inglês. To present our speaker today, which is Ricardo Campos, comes from the CNRS from Toulouse, the University of Toulouse, and he will be talking to us about the topology of configuration of spaces of points. So thank you, Ricardo, for accepting our invitation. It's a pleasure to have you presenting the CIM Colloquium. Please.
Thank you very much for the invitation. Thank you to you all for being here. Thank you for forcing me to give this talk in English. Otherwise, it's wouldn't be very convenient for you, but mostly for me. So today I want to tell you the story, the story about topology of configuration spaces of points, and the way we use algebra to pure algebra to study topology. So feel free to interrupt me with questions either in English or in Portuguese. Whenever you feel like I might be speeding up too much. I'm not so used to giving talks with slides, but the format is what it is. So what's the outline? I want to start with or maybe a main motivation for studying these configuration spaces, which are the embedding spaces. Then I'll talk about the main player of today's talk, which are the configuration spaces of points. And then I'll proceed to talk about modern techniques that we use to study these spaces, namely this rational homotopy is mentioned in the abstract. So embedding spaces, what are they? Imagine that embedding spaces or embeddings concern the way we can have a small manifold, a small space, say, inside another big space, and how to put it in there without any sort of self-process. To be a bit more precise, we can imagine the big space to be a big manifold, small space being n small manifolds, and an embedding is an injective map from n to m. And then the condition is also all this is smooth. You don't want to allow you want the derivative to also be injected. Say. Here you see the picture of what would be an embedding of R into R2. So what is this? It's just a curve inside the plane. Everything is smooth, so the curve has no spikes. And it's an embedding, so there is no self-process. So it's just a curve that doesn't intersect itself at any point. So it's the example of one embedding. We can consider the set of all possible embeddings of, say, in this case, R into R2. What's maybe not obvious is that this set actually comes with a topology. So there is a notion, this so-called CIM topology or Whitney topology. So we don't want to think of the set of all embeddings. We want to consider it as the space, the topological space of all embeddings from one manifold into another. I could define what exactly this topology is, but instead of defining it, I think it's maybe intuitive what this topology should do. So we have here an embedding. A topology is a way to say how two things are close to one another. So I think it's more or less intuitive how this other orange curve is close to the other. So if you wiggle it a bit, you have two embeddings that are close together, and the cylinder around it, you can imagine it's an open neighborhood of the first embedding. So there is a notion of one embedding converging into another. Hopefully this is clear. Again, feel free to interrupt me whenever you want. Embeddings are maybe not obvious that this is something quite complicated. You imagine one embedding is just one space hinting inside the other. But what's actually very complicated, it's hard to overstate how complicated, incredibly complicated this is, the topology of the entire embedding space. So, just to persuade you how complicated this problem can be, consider the specific case of knot theory. I imagine that we've all encountered knot theory in our lives at some point, at least in as a recreational mathematics. What is knot theory? Well, for normal people that you find on the streets, they will probably say a knot is just, maybe not in these words, but they will say a knot is an embedding of R, the line, in space. For mathematicians, weirdly, we say that the knot is not a line, but it's a circle. It's the way a circle can sit inside of normal space. And then, again, we have here two different knots, the trivial knot, which we call a knot, and there is the trefoil knot, maybe the simplest one that is not trivial. And in some sense, knot theorists will say that these two knots are different, but the question is, in which sense are they really different? They are embeddings of the circle in space. But in some sense, both of them are circles. So the way to say this is different, it depends who you ask this question to. If you ask this question to a knot theorist, will say, oh yeah, these two are different because there's no ambient isotropy connecting one to the other. Today, since I'm talking about embeddings, I want to say what this is from the point of view of these embedding spaces. So both of them are objects in this embedding space from S1 into R3. So S1 is a circle. And what does it mean to say that these two knots are different? It means that a path in this space of knots, in this embedding space, it's kind of moving your knot a little bit. But this path should somehow still be inside of the embedding space. So it cannot, at some point, pass by some non-injective function. So what this means is when you're moving your circle around, you're not allowed to cross itself. So in other words, you will say that two knots are the same if you can connect them via a path in this embedding space. Hopefully, this is more or less intuitive. But another way to rephrase what I just said is that knots are essentially the same as equivalence classes of paths in these embedding spaces. So, yet in other words, the set of knots is just the connected components, the path connected components of this topological space of embeddings from S1 into R3 space. And yeah, depending on your background, this can be a bit weird. Usually when you study topological spaces, maybe you don't think that studying their connected components is a very interesting question. Actually, many times you might even, depending on your background, assume that the spaces you work with are connected. In this case, understanding the connected components of this one topological space of embeddings from S1 into R3, it's to make it simple and hopefully not offend anyone, is an entire field of mathematics. It's understanding the connected components of the embeddings of S1 into R3 is knot theory, to put it in simple terms. Right. So, given this, and since it's such a simple example of two manifolds, you probably think that it's hard to make any sort of general claims about embedding spaces if you don't specify. So for very complicated manifolds. Already here we can say much. What can we say for arbitrary and embedding? Yeah, you would be right, first of all. But there are tools to study these embedding spaces. And one of the tools comes from the works of Tom Billy in the 90s. That is the so-called calculus of functors, functor calculus. It wasn't actually developed with intent of studying embedding spaces, but the idea applied to these embeddings is what? If you have one specified embedding of the small manifold inside the big manifold, what you can do is you sample some points, a fixed number of points on the small manifold. What does this give you? Well, since the small one is inside the big one, this also gives you a sample of points inside the big manifold, right? And this has an important property, which is since everything is injective, points that were distinct in the original manifold, they remain distinct in the final target manifold. So in a way, there is a map from configurations of points on the small manifold to configurations of points also on the big manifold. You can do this for any specified fixed amount of points, n. And so therefore there is this sort of evaluation from embeddings into maps on configurations of points on each manifold. And the big theorem that I don't actually need you to understand, but it's the motivation for having configuration spaces of points in all this story, is that, so this is a theorem of Goodwill and Weiss from 99. This tells you that actually understanding this evaluation map for which n, well, sort of for all n combined, I'm not going to make this precise, under some dimensionality conditions. So if the difference between the two dimensions is at least 3, it tells you that you can know a lot about the embeddings, the entire embedding space from n to n. This is actually, you have enough information to capture its homotopy, whatever this is. So what I want to use this theorem for is an excuse to tell you what I actually was working with, which are configuration spaces of points, the title of the talk. Awkwardly, if you see this dimensionality condition, you have that the dimension of the big manifold minus the dimension of the small manifold should be at least 3. If you think of knot theory is the embedding of the circle, which is one-dimensional, into space, which is three-dimensional. And 3 minus 1 is 2. 2 is not at least 3. So this doesn't actually do much for knot theory, at least not directly. But okay, in any case, I only talked about this to show you that the situation of embeddings can be quite complicated. But yeah, this co-dimension thing of being above 3 or below 3 is kind of a breaking point in all this.
Sorry, the small n is the number of points.
Yeah, the smaller n is the number of points, okay. And I will actually get a lot more precise next because I'm going to talk about configurations of points. So in fact, the last slide, it's not actually fundamental in any way to understand. But if you do have questions now, so configuration spaces. What are they? The intuition is what you see here in this picture. Fix n, a natural number, which will be the number of points. And now fix m, a very nice space. So assume always it's a smooth manifold. If you want, you can assume it's compact. It's as good as you want. Configuration space of n points on a manifold is what? Is you pick n points there, but you have one condition. You don't allow the points to collide. They should not take the same place. So if you want to see this as an embedding, you can also see it as a very basic case of an embedding. It's the embedding of the discrete set of points into the manifold. So in particular, it's a topological space because it's an embedding, but you don't need to know anything about this C-infinity topology or anything. In fact, what is this really? If M is your manifold, a configuration space is just a subset of M to the power n. And it's what you get when you remove what's called the fat diagonal, which is the collision locus. It's where at least 2 points coincide. So what you're actually doing is you're taking M to the power n. You remove this diagonal, it's a closed set. So actually what you get is an open submanifold of M to the power n. So geometrically, it's really not a complicated object. It's finite dimensional. It has tractable geometry, and you know what the topology is because it's the induced topology from M to the power n. What might actually be very deceptive is that these spaces are still very complicated to study. But now at least we can look at some low-dimensional examples of this. So for instance, what is the configuration of one point on a manifold? The point is on a manifold. There is no condition of overlapping. So configuration of one point on a manifold is just M itself. More interestingly, if what is the configuration of 2 points in Euclidean space in RD? Well, you need to know where the first point is located. Maybe say the first point is anywhere in space. So there is an x to the an r to the power d worth of choices where to put it. And where is the second point? Well, the second point can be located almost anywhere. It just cannot go in the same place where the first one is. So one way to describe the position of this second point is using polar coordinates. First, we specify the angle that it makes with the first point. So it's a sphere worth of places to be located in. And then you specify the distance, which is a positive number. Strictly positive, since it cannot be zero, it cannot coincide with the same point. So in other words, what we have is exactly that the configuration space of 2 points in RD is homeomorphic as a topological space to RD cross a sphere of dimension d-1 cross the positive numbers, the positive rates. And yeah, you have the picture there of what happens in dimension 2. So you specify x1, the angle, and the distance. This gives you all the data you need to recover the configuration of the 2 points.
And the order of the points?
Yes, yes, this is the orders configuration. Okay, there is also another thing that you can imagine, which is where the points are indistinguishable. So this would be the quotient by the natural action of the permutation group of Sn in there. It would be the quotient by this action. So it's also a space that people study. But yeah, in a way, this is the more general one because the other one is obtained as a quotient of this.
Sorry.
Yeah.
How do you fix theta equal to 0? You have one direction fixed. Yes.
Yeah, maybe you have to make some choice there.
Some reference.
Yes, but at the end of the day, up to homeomorphism, you get exactly the same space. But yeah, I agree that there is some choice in the homeomorphism you choose, and maybe yeah, I agree. There is some choice. It doesn't affect the topology. Right. So at least it's a place where a situation where we can describe everything explicitly. Now let me just mention, since this might we're speaking to a broad audience, so some of you might have different interests. Some of you working in group theory might be familiar somehow with what happens on the plane. It's known what is the configuration, more or less known. What's the configuration space of points on the plane? So what is this? You can imagine that you have your endpoints maybe aligned on the plane, and you can ask what is a path in this configuration space to sort of exactly the same configuration a bit downstairs. And sure, you can do the trivial thing of just going straight down, Or you can wiggle things around, like you see in the picture. And it turns out that this is related to the pure braid group. In fact, the pure braid group is a fundamental group of this configuration space. If you're maybe inclined more, I don't know, motion planning inclined or into robotics or anything, there is also a very trendy topic, which is configuration spaces of points on graphs. So why is this relevant? You can imagine a bunch of situations where this appears. You have some assembly line with some treadmills, or maybe you have a railway system where things can only move along one dimension, and you don't want your trains to collide. So it's a configuration space. If you don't want train 1 and train 2 to crash into each other. Then the question would be, take this simple graph. Okay, maybe you will argue it's not a manifold. Graphs are really manifolds, so that's not the issue here. You have maybe the simplest graph that you can imagine that's not just a straight line. What's the configuration space of 2 points on this graph? Well, maybe you'll answer, yeah, it's that. Here's 2 points on the graph, and yeah, that's not the configuration space. It's one specific configuration. We're interested in the space of all such configurations. So what kind of topological space is this? And I will let you think for 5 seconds what the topological space looks like. So it's this. If you've never seen this before, it's surprising that just take this graph and what the hell do you mean by this this configuration space? It's this star-shaped object. It's actually very visual. You zoom in on it, and in this sort of flat star, the horizontal star, the vertices of it, they represent configurations where points are maximally far apart. There's 6 ways the points can be maximally far apart, points 1 and points 2. And so yeah, I am using the pointer, apologies to the online audience. Then if you look at this one down here, and you start moving in this direction, what you're doing is you're making point number 2 approach the center. But then once point number 2 reaches the center, there is actually a new direction it can travel to. It can travel in the direction of point number 1, which in the picture is represented by going vertical upstairs. Yeah, there is a hole in the middle of this space. This hole is supposed to represent the configuration where the 2 points are exactly in the middle of the graph. So it's visible. So the point is not that point is not there. Yeah. So hopefully this is already enough of an argument to justify that configuration spaces can be complicated objects even in very simple cases. So how do we study them? Well, I study them personally from the point of view of algebraic topology. And if in topology you're interested in studying spaces up to homomorphism, so squeezing, stretching, not breaking, in algebraic topology, you're typically interested in studying spaces up to homotopy equivalence. So you're now also want to study spaces up to retractions. What do I mean by this if you haven't seen these notions before? What I mean by this is in algebraic topology, you say that if you have, for instance, the entire Euclidean space up to homotopy, this is the same as a point. So there is you can take the entire space and retract it all down to a single point. So this is not more interesting than a point. And in fact, if you look at the positive reals, this as well is just homotopy equivalent to a single point. You can retract it down to a unique point. So if we revisit the configurations of 2 points in space, as we saw before, in fact, you'll see that the only surviving piece of this configuration space up to homotopy equivalence is just the sphere. So fundamentally, what I'm saying is, if I have 2 points in space, fundamentally the only thing that they can do is they rotate around each other. So if I have one, the other one can move freely around, but we can kind of retract this to, as in the picture, to some fixed circle around it. So it's really only the angle, the only relevant thing that survives up to homotopy equivalence. Just to illustrate a bit more the story of homotopy equivalence, in this case, these two, you can retract the triangles that go up, you can retract them down and make the star flat. The star is a hole, so you can't contract it down to a point, but you can do the same trick and just pick some circle around the hole and then retract everything to this circle. So in fact, this configuration space is also a circle, which is something really not obvious if you see it for the first time. Right. So configurations of points, they're very easy to define, but they've been studied from the point of view of algebraic topology since the 60s. I think the first people that were studying them were Fadel and Neuwirth, who computed a bunch of algebraic invariants for them. And since then, the question that lingers is the following. Does the homotopy type of the configuration space of points, does a homotopy type of the manifold determine the homotopy type of the configuration space of points? Just to put it more precisely, if you have two manifolds that are homotopy equivalent, you can look at the configuration spaces, say for a fixed number of points of each. Are they also necessarily homotopy equivalent? And this is not an obvious question. Why is this not an obvious question? If you take this idea that homotopy equivalence is just retractions, well, retractions are things that are really not injective, but configurations of points are injective things. It might happen that you have 2 points that were distinct in some configuration space, and then you do some retraction, then they end up in the same place. So they're no longer in the configuration space. So there's no obvious way homotopy equivalence of manifolds will translate to a homotopy equivalence of the respective configuration spaces. So in fact, this has been an open question for a very long time. I list also the names of Salvatore and Mongoni from 2005 because they realized that the conjecture was false without some objective, namely without the simply connectedness assumption. But as stated, this question is fully open for 21 years now. So what is my contribution to this story? My contribution here is to say that, well, I can say much about this conjecture, but I can say something about a very similar conjecture. I can say that, so it's a result of myself and Thomas Wilfacher. We can say that if your two manifolds were rationally homotopy equivalent, whatever this means, then their configuration spaces are also rationally homotopy equivalent. Being rationally homotopy equivalent is a weaker condition, so the conclusion is weaker, but the premise is also weaker. If I want to explain what this is in 10 seconds, the idea is that homotopy equivalence is something over the integers, rational homotopy equivalence is something over the rational numbers. So they kind of disregard torsion that might appear in spaces. So I guess now I will need to say something about rational homotopy theory, but if you have some questions before. Yes.
I'm just curious about your example of 2 points. How to understand this? Is it?
Yes. Yeah. What is this? It's yeah, it's essentially saying that apologies for the online audience, but it's saying that yeah, if I have 2 points here, kind of what is the circumference that you're doing? You're kind of doing this is making a circle. And it's hard to give more details. I don't know. This is my intuition on what's going on there. A rigorous proof is in fact done by these pictures. Yeah, sorry, it's hard for me to say much more than that. But yeah, there is fundamentally some circle that the 2 points can make with each other, even though weirdly they're living in a one-dimensional graph.
Ainda conseguiste me perguntar. Ana, queres ligar o microfone e perguntar?
Deixa eu ver se consigo. Hello. Can I ask you something, please? On your slide on
Perguntamos se eu consigo ouvir, se o microfone está ligado, podemos ouvir. Ana,
Hello?
não consigo ouvir.
Supostamente tem som.
Tem som. Posso falar?
Só escrever com
Se aumentar o som. Ana, consegues escrever a pergunta?
Uhum.
Devia ser aqui. É que seguramente te faz feedback.
Estamos a ver no browser e aquele não ter alguma permissão.
Som, microfone.
Mas é isto, é o speaker, pode tentar mudar o
É o
speaker.
terceiro, é?
Pois.
Também mais. Mais algum? Este aqui, não é? Ok, então. Podes pedir para falarem para ver se ouvimos?
Tô. Hello?
Agora
Então,
Agora ouvimos. Sim, força.
ouvem?
Sim, sim.
Muito bem.
Ok, obrigada. On your slide on configuration of graphs, which is, I think, nope, no, before this one. Yes, the first one. Yes, yes, yes. I did not understand the construction. Can you give me some reference, please, as this is... I would like to understand these. So I'm lost in this construction, but is there any reference you can give me? Something like that, so that I can understand? Hello? I'm not listening now.
Consegues ouvir?
Agora sim. Ouviram a minha pergunta, Jorge? Jorge, ouviste a pergunta? Não estou a ouvir nada, nada, nada.
E agora?
Agora sim.
Pronto,
Sim.
então se calhar deixamos assim e deixem-se não ouvirem. Yeah, so I can't, in any case, it's just to say that I can't give the references right now because this is actually a very orthogonal topic, the configurations on graphs. it goes in a very orthogonal direction to configurations of on manifolds. But I don't know, at least this one specific particular picture, if you think exactly what okay, you can at least fix the three extremal points where the points are maximally far apart. This gives you the 4 edges, that's the 6 vertices in the star downstairs. And then there's essentially 2 different directions you can go. You can either make point number 2 approach the center or point number 1 approach the center. So this sort of makes the whole flat star. And then once you get to the center, yeah, now there is a third direction they can go to, which makes the vertical triangles appear. But maybe I can after the talk just give some links. I forget there's some very good reference for people that are doing these configuration spaces on graphs.
Well, Campos is also replying to her, so maybe
Okay.
he put something on the chat. So
Okay, maybe then I can proceed.
you can proceed. Yes.
If Carlos allow me to dodge the question. Yeah. So rational homotopy theory. What is this? If maybe before this, I should tell a bit more about normal algebraic topology, rational homotopy theory. So algebraic topology is what? It's not just doing homotopy equivalence. It's actually the whole idea is to replace topology by algebra because well, topology is very hard to keep track of continuous maps and blah blah. And at least with algebraic objects, well, it's not easy, but I mean, many times in mathematics we find ourselves replacing something with algebra. You have a different sort of tools to address this issue. In algebraic topology, you associate topological spaces, some algebraic invariants, fundamental group, homological, whatever. They are invariant because they're invariant under homotopy. So specifically, the thing that we have, and you don't need to fully understand what I'm saying, but given the topological space, you can take its cohomology, its singular cochain points. It's some ring, some differential graded ring, and the statement is that if you have 2 topological spaces and the homotopy equivalence between them, you look at their singular cochains, and this is a map of differential graded rings. If it's a homotopy equivalence in the topological side, it's a quasi-isomorphism in the algebraic side. This is, I mean, it's a statement that the map induces an isomorphism in homology. It doesn't matter exactly what it is, it matters that there is a corresponding notion of equivalence at the algebraic side, and it's this quasi-isomorphism notion. In one sentence, the idea is that you have topological spaces. You send them to associate to topological spaces some algebraic object. This algebraic object is a ring, so it's somehow something living over the integers. And yeah, in principle, it's something computable. I give this to my students of algebraic topology. They always ask me the same question, which is, okay, great, this is an invariant of homotopy equivalence. So we can, if I have 2 homotopy equivalent objects, I have the equivalent algebraic incarnation. Does it go in the other way, in the other direction? If you have 2 topological spaces with quasi-isomorphic homology rings or cochain, singular cochains, are they necessarily homotopy equivalent from the side? And the point is that, unfortunately, no, this is not true, but it becomes true if you work with the rational numbers. So to summarize, this philosophy of replacing topology by algebra works well if you're replacing your topological spaces by their code chain, singular code chains with values in the rational numbers. So in some sense, topological spaces are the same as commutative differential graded algebras over the rational numbers. If this was too much, I will only spend 5 seconds on this slide to just be able essentially to say that there is a theorem by Quillen and Sullivan in the 70s. It's the creation of rational homotopy theory that tells you that indeed there is some sort of equivalence subcategory between. There is a formal notion, formal way in which it's really true that topological spaces and rational algebras are the same. But I'll only come back to this slide if you force me to.
Can I ask one question?
Are you forcing me to go back to the slide? Yes, you can.
Okay, just to know what does the greater or equal than 2 means in the homotopy topological category.
Simply connected. So
okay.
Okay. Only has homotopy groups starting at 2.
Okay, thanks.
Connected, yeah. And also for algebras, then you should assume that they live in degrees starting at 2. So the analogy would be that so if you're not into algebraic topology, but if you're a differential geometer, what we're saying is you have you can replace studying smooth manifolds up to homotopy equivalence, up to rational homotopy equivalence by studying its de Rham complex, which is not just a complex, it's an algebra because you have the wedge product, so you can take a wedge product of differential forms. It's a differential graded algebra because this is compatible with the de Rham differential. Understanding this algebra up to quasi-isomorphism, so maps that induce isomorphism in cohomology, is the same as understanding the rational homotopy type of your original manifold. So for differential geometers, maybe it's an easier way to see what this means. And yeah, in the simply connected case. And in fact, that's what we do in our main result. So the result before is actually kind of a corollary of this ongoing work by spanning over multiple papers and multiple people. So names that I have there is myself, Julien Colombier, Najib Mifisi, Pascal Ambres, Thomas Wilbacher, and it's still somewhat ongoing. Our result is that we want to understand this rational homotopy type of configuration spaces of points. In other words, we want to understand maybe their de Rham complex with the algebraic structure. And what we construct is, so what do I write? We construct a commutative differential graded algebra. It's not over the rational numbers, it's over the real numbers. It doesn't matter, it only matters that it's a field of characteristic 0. Also, rational homotopy theory, it's maybe an easier phrase to understand than real homotopy theory, since real has other meanings. Anyway, what we do is we construct some algebra that we call graphs n. So n should be the number of points that we want to understand. And this is supposed to capture completely the rational homotopy type of the configuration space of points. To say a bit more precisely what I mean by this, there's a differential graded algebra, something with a product and the differential. It's conveniently called graphs because it's made out of graphs. And this comes with a map to the de Rham complex of configuration spaces of points on a given manifold. This map is denoted by an integral sign for mysterious reasons. And this map is a quasi-isomorph. So what is this and what does this do for us? So what does this look like? It's made out of graphs. So this is an algebra. So it's an algebra. First of all, it's a vector space. As a vector space, it's a vector space with a preferred base. It's given by by graphs. Graphs have some certain number of labeled vertices that correspond to the amount of points that we're sampling. And it has some other data. It has some unlabeled vertices that are here black, some decorations by some topology classes on the manifold. They look like this. And then you ask me, okay, how is this a vector space? How can I sum two graphs? You don't. I mean, you do, but it's a formal sum. They're not. It's really the vector space whose basis is some graphs of this kind. And we didn't make up these graphs. These graphs have been used by people doing quantum field theory for a long time. There are these Feynman graphs appearing in perturbative extensions. What we did is we made some algebraic object out of these graphs. And they have the advantage of being fully explicit. Okay. A caveat, you need to understand something about your manifold, but if you don't understand your manifold, you shouldn't try to understand its configurations of points. Also, it's finite dimensional under some mild constraints, which is good. It's something that you can give a computer to do calculations with. So the point is that we use this result to prove this homotopy invariance that I mentioned before, because all of a sudden this becomes kind of a combinatorial problem. We have two manifolds. We look at their configuration spaces of points. We can model them by some graphs. If we look at the graphs and they look more or less the same, then it's because the configuration spaces of points are the same. This is very, very vague, but once we have this, the actual proof boils down to a combinatorial question about graphs, which is quite interesting.
Just if the graphs are embedded into the manifold.
No, graphs on the plane. These are graphs. It's graphs from. It's the data that I'm saying. These are graphs. They leave as graphs. You have a fixed set of labeled vertices, which correspond to the amount of points that you have from the manifold. So far, there's no data from the manifold. They have vertices, like vertices. This has nothing to do with the manifold. Where does the manifold go in? The manifold goes in because there's these decorations, and these decorations are depend on the cohomology of on the manifold. So these are decorations by cohomology classes of the manifold. And then what else is there? There is a product. This product has something to do with edges. It's not complicated. And there is a differential, and in the differential, you actually see the geometry of the manifold appearing. So that's actually where the whole complication exists. But yeah, no, these are combinatorial graphs with some weird geometrical data appearing, but they're not embedded anywhere. They're not planar. They're graphs. So it's like all the graphs when you become combinatorials, but we say that these are graphs. Right. So, I mean, of course, I'm not going to give a lot more details about this theorem, but at least I would like to use this opportunity to tell you a bit about what is complicated and what is easy about this problem. So this statement is about the existence of some map that satisfies some properties. So this is essentially, there are essentially three main steps in this stuff. There's constructing what exactly these graphs are. I said that this has a complicated differential. It's a non-trivial endeavor. There is actually constructing them up. So a relation between graphs and differential forms should be something slightly weird. And there is, once we have all of this, you need to show that this is still an equivalence, quasi-equivalent. I would like to tell you a little bit about the second step, justifying some of the things we see. So I'll tell you what this formula looks like, not caring about, you shouldn't care much about what it does, but you should get a flavor of what it is. So the idea is that two graphs, given a graph, I associate to it some differential form. It's given by some explicit, somewhat explicit calculation. It comes with an integral sign. It has some differential forms that are this propagatory, this universal AKS set quantum field theory. It doesn't matter. The focus is really on the integral sign. We're integrating over something, and what are we integrating over? We're integrating over configurations of 4 points to configurations over 3 points. It's an integral that exists in configurations of points. Okay, that's the thing you should retain from this formula. Really nothing more. But we're integrating, and if there's analysts around, they will come because okay, maybe we can assume that our manifold was compact. We can integrate on compact manifolds, differential forms. It's great. But we're not integrating over M. We're integrating over the configuration space of M. This is open. And integrating over open sets in principle carries analytical problems, right? You need to show that integrals converge, which is, I mean, in principle, this formula is not well defined if you don't know if integrals converge. So you can imagine, oh, now then there is some analytic argument to show this converges. But no, there is actually something very different that we do, which is inspired by some tools coming from algebraic geometry, namely the so-called Fulton-McPherson compactification. What is this? I said that the problem is that our space is not compact. It's not compact. Why? Because points cannot, remember, points cannot collide. So the sequence of points, point number 2 approaching point number 1, this has no limit. A way to solve this is to embed, to place our configurations inside some bigger compact space, and then maybe try to work there and see if you can make integrals make sense there. This is what's called a compactification. You go into a compact set. Configurations of points, they kind of naturally live inside of a compact set. You can just take the compact set being, well, now we forbade points from colliding, now we allow them to collide again. Yeah, but this doesn't really work. This has a bad homotopy type. This m to the power n is something very, it's too simple to work. But the strategy that does work is a slight variation of this. There is this Fulton-McPherson compactification. What does it do? Maybe the slide doesn't explain as well as my hands. But the idea is that now you allow points to collide, but when they collide, they remember the way they collided. So it's different to collide like this or to collide like this. So they retain some sort of tangential information. I guess algebraic geometers would say that this is a blow-up. It's not blow-ups typically produce projective space, but it's a real blow-up. So there is a difference between colliding from this side or colliding from the opposite side. It's probably better with a picture. The compactification of 5 points, of the configurations of 5 points on the torus, is, you see normal configurations, but now you allow new configurations where points 2 and 3, they collided there, but they still remember how exactly they collided. So from the point of view of 1, 4, and 5, 2 and 3 are at the exact same place. From the point of view of point number 2, he can say, oh yeah, 3 is there. It's not there, it's there. I don't know exactly the distance. I am to 3, like we share no, yeah, there is no distance that can be measured, but I know that you're there in that direction. So this kind of solves the problem if you only have 2 points. But then the problem is that what happens then if point number 4 decides it wants to join points number 2 and 3, right? And then sure, it can go to the exact same location. But then there's still a difference that now point number 2 can measure sort of the relative distance, can say which one between 4 and 3 is closer together. They can measure some sort of relative distance. And the problem is that this is still not compact. 4 could now still approach 3 more or 2 more. So this doesn't work, yeah?
Yeah, I have a question. If you do that for all points, don't you get the configuration space because all of the points can be distinguished their positions? If you went one by one?
No, you are doing it for all points. The problem is that what you actually need to do is some sort of iterative blow-up. So in fact, what you want to do is you want to now allow still a further level of infinitesimal proximity, where, so in this picture, from point number 1 and 5, everyone is at the same place. But now from the point of view of 2, 4 and 3 are at the exact same place. But now from the point of view of 4, 3 is still in that direction and not in some other direction. No, this is not the normal configuration space. In fact, what is this? This Fulton-McPherson compactification is now a compact manifold with boundary. But the boundary is when the 2 points go together. But then the boundary has boundary because the points can further go together. So this is what's called a manifold with corners. This is essentially magical. It solves all our problems. So first of all, it has the correct homotopy type. It's standard fact in topology that manifolds with boundary are homotopy equivalent to their interiors. And the interior of what is the interior of this? The interior is when you're not on the boundary. So it's when points don't share a position. So the interior is exactly the normal configuration space of points. So this has the right homotopy type. This is compact, which is exactly what we were looking for. So now we can integrate differential forms. No problem of things exploding at poles or anything. And then, yeah, we have actually very good control over what's going on at the boundary. We're doing these fiber integrals, so we can apply Stokes' theorem or Stokes' theorem for fibrations, and this is what is used to show that you have Stokes' theorem gives you the compatibility with the differential on the graph side and the Durham differential on the differential form side. Yeah, so hopefully I was able to give you a bit of an idea what kind of tools exist in these configurations of points. Thank you for your attention, and I welcome any questions.
Either here or at home. I think now you just can turn on your mic and ask your questions. Should the system be working properly? Yeah, well, please.
Kind of a naive question, which maybe you gave a hint to why at the end it's like too naive to work at the end, which is, I was thinking in the beginning that you could kind of understand these recursively by thinking you take the n-fold Cartesian product of your manifold. So you have that diagonal, and then you have endpoints, and maybe some of them coincide, and you map it to a certain configuration space, and then you map the other one. So you kind of see the whole n-fold Cartesian product as kind of a union with multiplicities of these smaller configuration spaces. And this, I mean, naively could maybe recursive allow you to.
Yeah, no, this is it's not naive. So you can express configurations of multiple points even with these restrictions. Can categorically you can draw some sort of diagram and express things in terms of certain push-outs and pullbacks. Yeah, and then this gets very complicated when you start having more than 2 points. But then you start running into a bunch of issues. Since you're interested in homotopy type of these spaces, you want the relevant push-outs or pullbacks to be homotopy push-outs or homotopy pullbacks. The naive thing that you do doesn't work directly. So I'm not saying you can't do something with this. I'm saying it's not as trivial as one might think, just because you can write a diagram. There's maps all over the place. You have from configurations of 7 points to lower number of points. You have maps of forgetting points. You can also create maps in the other direction, add a random point at a specific position. So there is stuff that you can do, but what you can do naively doesn't give you as much information as you would expect.
Could there be a bound, effective bound of the number of points that you need to go back from the rational equivalence in configuration points to the
Back to the problem of embedding spaces or to normal.
if I understood it well, you're saying that to the rational equivalence or multiple equivalence of manifolds is equivalent to that of configuration spaces, right?
Yeah. So
My question is if you could, knowing some information on the manifolds, have a bound on the number of points that you would allow you to take the conclusion in the reverse direction.
yeah, there's no general statement, but there is I think specific computations that people do for specific manifolds. But yeah, it's hard to make any sort of general plan. What I thought originally you were asking is whether you can looking at just a finite amount of points with an upper bound, you can conclude something on embedding spaces from the motivation, and the answer to this is also no, at least in full general. I don't know if some special cases, the answer might be yes. But in any case, I'm answering a question that was not your question.
Yeah, I have also one question. We saw that if we have, for example, RD, the configuration space is homotopy to RD times the sphere and so on. So I was wondering if we could describe generally the product of manifolds and then the configuration space of the product. Like if you have two manifolds, one examination D and M, then the configuration spaces will have the formula to express them.
Oh, the Cartesian product of two manifolds.
Yes, exactly. With the configuration space. Generally, if you have a way to describe it.
No, I don't think. No, indeed. Well, if you look at the example that you gave, for instance, configurations on R3 and the configurations of R7, they're well understood. Their products are configurations of R10, but one you get a 2-sphere, and the other you get a 6-sphere, and somehow in the product you get a 9-sphere. I mean, maybe in this specific case you can do something, but I don't think there is any sort of general formula that you can get. Be very simple to do.
Let me ask if there is some question for those who are online. Is there any question?
Well, I was asking one question. I don't know if you can hear
Yeah,
me.
quick question. Yes.
Okay, if you can say something about the boundary map in that graded algebra graphs N, and if there is some simplification in the case that the cohomology of M has only even degrees. I mean, it's 0 in odd degrees.
You know, this boundary map is actually really complicated. It itself, that's what's deceptive about these graphs. It's that they're really simple and direct to describe the basis, the products, but the differential itself depends on some integrals. So in fact, you might even wonder why do we do this over the real numbers and not over the rational numbers? It's weird, but like graphs is in principle something that even exists over the integers. But in fact, no, the differential, since it's the differential will have some coefficients in there that come from some integrals from configuration spaces. The graph algebra itself, it will not live over even the rational. So it really needs the real numbers. You might have pi here and there. Now, with some simplifications, you can get some control. For instance, this simplification of assuming that the manifold is simply connected already is a bit helpful because it gives you some control about the complicated terms that can appear, but you still can't fully describe it. And assuming that it lives in even degrees, I mean, guarantees that some terms will vanish, but in principle, in general, it will still be something very, very complicated. So it's not helpful in this generality. For specific cases, you might be able to say something about it, but not in general. Even in homology concentrated in even degrees.
Okay. So I think we should all thank Ricardo once more. And thank you all for appearing here. It was a pleasure to welcome you. Well, welcome you. And for those at home as well, thank you for joining us. And then soon we'll resume with the CIM meeting. Okay, thank you so much. Goodbye.